Consider the ground beneath you, not as a metaphor, not as poetry. Consider it as a physical object. A continuous shell of solid rock, thousands of kilometers thick at its deepest, wrapped around a core of molten iron and nickel that rotates at a different speed than the surface you are standing on. That shell is not one piece. It is broken into fragments, tectonic plates, and those fragments are moving. Not slowly in the way a glacier moves, where the motion is visible if you wait long enough, more slowly than that. At roughly the rate your fingernails grow, centimeters per year. A speed so far below the threshold of human perception that your body has no way to know it is happening. And yet, that motion is the single most consequential fact about the planet you inhabit. It builds mountains, it opens ocean basins, it concentrates mineral deposits, it controls the distribution of volcanoes, and it produces earthquakes. Every earthquake on Earth is a direct, unavoidable consequence of plate tectonics. The plates move. Where they interact, they lock. Where they lock, stress accumulates. Where stress exceeds friction, the rock breaks, and the energy of that breaking radiates outward. That is the fundamental cycle. It is not mysterious. It is not unpredictable in its broad strokes. The largest plate boundaries on Earth, the Pacific Ring of Fire, the Alpine Himalayan Belt, the mid-ocean ridge system, produce earthquakes at rates that can be calculated, averaged, and mapped. Seismologists can tell you, with considerable accuracy, how many earthquakes of magnitude 6 or larger will occur globally in any given year. The number is surprisingly stable, between 100 and 150, year after year, decade after decade, across the entire instrumental record. The planet is that consistent. It has a background rate, a baseline, a rhythm, but that consistency masks something strange, something that the public rarely hears about, and that even many scientists spent decades underestimating. The consistency of the global earthquake rate is a statistical property. It emerges from averaging over thousands of events across the entire planet over many years. It tells you nothing about any individual earthquake. It tells you nothing about the connections between earthquakes. And it tells you nothing about whether an earthquake in one place can influence the timing of an earthquake somewhere else. For most of the history of seismology, accumulating across the region was that earthquakes were essentially independent. A fault broke because of the stress that had accumulated on that specific fault over its own history. The stress field around it was local. The influence of a distant earthquake was treated as negligible. A faint vibration too weak to matter. A curiosity recorded on seismographs, but incapable of affecting the mechanics of a distant fault. That assumption was reasonable given the tools available at the time. Early seismometers were sparse. Global coverage was thin. The ability to detect small earthquakes was limited, and the physics of wave propagation, while well understood, did not obviously suggest that a passing wave could trigger a new rupture at great distance. The energy density of seismic waves falls off with distance. By the time a wave from a magnitude 6 earthquake has travelled halfway around the planet, its ground motion is measured in microns. A human hair is roughly 70 microns thick. The wave moves the ground by less than the width of a hair. It seemed implausible that something so faint could do anything at all to a fault holding hundreds of years of accumulated tectonic stress. Implausible, but wrong. The shift began slowly. In the 1970s and 1980s, scattered observations emerged of small earthquakes apparently triggered by distant large events. The evidence was tantalizing but inconclusive. The triggering, if real, seemed weak and inconsistent. Then, on June 28, 1992, the Landers earthquake struck the Mojave Desert of Southern California. Magnitude 7.3, a major event by any measure, but not unprecedented. What made Landers a turning point was not the earthquake itself. It was what happened afterward. Seismologists had placed temporary instruments across the western United States to monitor aftershocks. Those instruments recorded something unexpected. As the surface waves from landers rolled outward across the continent, distant seismometers began recording small earthquakes at sites that were nowhere near the rupture. The timing was too precise to ignore. The bursts of seismic activity began at the exact moment the surface waves arrived. Not minutes later, not hours later. At the moment of arrival, Yellowstone, more than 1,000 kilometers away, responded. The Geysers geothermal field in Northern California responded. Long Valley caldera responded. Sites across the Pacific Northwest responded. The pattern was unmistakable. The Landers earthquake had reached across the continent and triggered small earthquakes on faults that had nothing to do with the original rupture. The term that emerged for this phenomenon was dynamic triggering. Dynamic because it was carried by the dynamic stress of the passing seismic waves, not by permanent changes in the background stress field. Triggering because the distant earthquakes occurred at the moment the waves arrived, with a timing that could not plausibly be coincidental. The discovery forced a fundamental revision in how seismologists thought about the connectivity of the Earth's fault system. Earthquakes were not isolated. They were linked by the waves they generated, waves that travelled through the planet's interior and along its surface, carrying the energy of one rupture to every other fault on Earth. The decade after landers saw a cascade of confirmations. The 2002 Denali earthquake in Alaska, magnitude 7.9, triggered seismicity across the western United States, including at Yellowstone, where researchers documented not just small earthquakes, but measurable changes in geyser eruption intervals. An earthquake 3,000 kilometers away had reached into the hydrothermal plumbing of Yellowstone and altered the timing of water erupting from the ground. That is not a metaphor. That is a measurement. In 2012, a magnitude 8.6 strike-slip earthquake in the Indian Ocean, the largest strike-slip event ever recorded, triggered earthquakes worldwide for nearly 6 days. The global earthquake rate remained elevated after that rupture, across every continent, on faults on the literal opposite side of the planet. The statistical signal was clear enough to be measured against the background rate. The planet had answered. So, here is the question that this documentary exists to answer, and it is a question that sits at the intersection of seismology, infrastructure risk, and human psychology. If the Earth's fault system is globally connected, if every significant earthquake sends waves across the entire planet, and those waves can trigger other earthquakes on distant faults, then what does that mean for the ground beneath the places where people actually live? What does it mean for the cities built on fault lines that are already loaded, already close to rupture, already waiting for a nudge? And what does it mean for the millions of people who live on those faults, most of whom have no idea that the ground they trust is in constant, invisible conversation with earthquakes happening on the other side of the world? This is not a documentary about fear. It is not a documentary about inevitability. It is a documentary about connectivity, about a planetary system that is far more integrated than most of us realize, and about what that integration means for the way we measure, prepare for, and ultimately live with earthquakes. The planet rings. It rings constantly, from thousands of earthquakes every year, most of them too small to feel, many of them too distant to notice. The ringing is faint. It is far below the threshold of human sensation, but it is real, and every loaded fault on Earth hears it. Some of those faults are in the middle of oceans, far from any city, where their eventual rupture will harm no one. Others are directly beneath major population centers: Los Angeles, Tokyo, Istanbul, Mexico City, Jakarta, where a large earthquake would kill thousands or tens of thousands of people. Those faults are listening. They are always listening, and the question that seismology has only begun to answer is this: when they finally break, Will it have been a distant earthquake that chose the moment? Let us move from the general to the specific, from the idea of global connectivity to the physical mechanism that makes it possible. Because if you do not understand the waves, you do not understand anything that follows. And the waves are not complicated. They are elegant. They are the purest expression of how energy moves through rock, and they are the reason an earthquake at the bottom of the world can touch a fault beneath your feet. When a fault ruptures, when two slabs of rock that have been locked together for decades or centuries finally lurch past each other, the energy released does not travel outward as a single pulse. It travels as several distinct families of waves, each with its own speed, its own motion, and its own range. The fastest are the P waves, P for primary. They are compressional waves, the same family as sound waves, squeezing and stretching the rock as they pass. A P wave moves through solid rock at roughly 6 kilometers per second. In granite, that is more than 20,000 kilometers per hour. They are fast enough to circle the Earth in about an hour. P waves travel through the deep interior of the planet, through the mantle, through the outer core, through the inner core. They are the first signal to arrive at any distant seismometer, the first knock on the door, the early warning that something has occurred somewhere. They carry relatively little energy compared to the waves that follow, but they are indispensable for locating an earthquake. The arrival time of the P wave at multiple stations, triangulated, tells you where the rupture happened. Slower than the P waves are the S waves. S for secondary. They are shear waves. They shake the ground perpendicular to the direction of travel, like the snap of a rope. S waves travel at roughly 3.5 kilometers per second in typical crustal rock. They carry more energy than P waves, and they are the waves that produce most of the destructive shaking close to an earthquake. But S waves have a critical limitation. They cannot travel through liquid. The Earth's outer core is liquid iron and nickel. When S waves from an earthquake reach the core mantle boundary, they stop. They do not pass through. They cast a shadow, a region on the opposite side of the planet where no direct S waves arrive. That shadow is how seismologists confirmed that the outer core is liquid, long before anyone could drill anywhere near it. The shadow is still there. Every earthquake produces it. It is a permanent feature of how waves move through the planet. The third family of waves is the one that matters most for dynamic triggering. These are the surface waves. They do not travel through the deep interior. They travel along the skin of the planet, the boundary between solid rock and air, or between solid rock and water. Surface waves are slower than both P waves and S waves, typically moving at 2 to 4 kilometers per second, depending on the frequency and the rock properties. But they are tougher. They persist. They carry large, slow, rolling motions that can travel astonishing distances before fading. And there are two kinds: Love waves, named after the British mathematician Augustus Love, shake the ground horizontally. Imagine grabbing a thick rug and shaking it sideways, sending a horizontal ripple running across it. That is a love wave. The ground moves side to side, perpendicular to the direction the wave is travelling. Love waves do not involve any vertical motion. They are purely horizontal, purely shear, and they can be devastating to buildings because most structures are weaker against horizontal forces than against vertical ones. Rayleigh waves, named after Lord Rayleigh, are different. A Rayleigh wave rolls the ground in a vertical ellipse. The ground moves up and forward, then down and back in a slow, circular motion. If you have ever seen video of the ground visibly rippling during a great earthquake, the solid earth moving like the surface of a pond, you are watching Rayleigh waves with your own eyes. They are the slowest of the major seismic waves, but they carry enormous energy, and they are the primary reason. Large earthquakes can be felt hundreds or thousands of kilometers from the epicenter. Now, here is the key. Surface waves are dispersive. different wavelengths travel at slightly different speeds. A surface wave that starts as a sharp, compact pulse will, over distance, stretch out into a long, drawn-out train of motion lasting many minutes. The long, slow, deep-reaching components arrive first. The shorter, faster components catch up later. The result is that a distant fault is not given one quick jolt and then released. It is worked on, flexed, strained, relaxed, flexed again, through a sustained passage of rolling ground motion. That matters for triggering. A fault that is already close to its breaking point might ignore a single sharp tap. But minutes of sustained, low-frequency shaking? That is a different matter entirely. That is the difference between a nudge and a sustained push. And it is why surface waves are so effective at reaching across the planet and finding faults that are already balanced on the edge. To understand how effective, consider the 2004 Sumatra-Andaman earthquake, magnitude 9.1, the third largest earthquake ever recorded by modern instruments. It ruptured more than 1,000 kilometers of the Sunda megathrust off the western coast of Sumatra, displacing the seafloor by up to 20 meters. The energy released was staggering, equivalent to the entire world's energy consumption for several weeks, released in a matter of minutes. The surface waves from that earthquake did not just circle the planet. They circled it repeatedly. Seismometers around the world recorded the Rayleigh waves passing, then recorded them again as they completed a full lap of the Earth, then again and again. Seismologists label these passages R1, R2, R3, and so on. Each number is another complete circuit of the globe. After the 2004 earthquake, the surface waves remained detectable for more than a week, circling the planet over and over, slowly decaying but never quite vanishing. The Earth rang like a bell for days. The 2004 earthquake did not just produce measurable surface waves. It produced measurable deformation of the Earth's surface from the normal modes, the whole planet oscillations that are the seismic equivalent of a bell's fundamental tone. The Earth has a set of natural frequencies determined by its size, its density, its elasticity. Strike the planet hard enough and it vibrates at those frequencies. The breathing mode, where the entire Earth swells and contracts as a single sphere, has a period of about 20 minutes. The rugby ball mode, where the planet stretches into an ellipsoid and then squashes back, has a period of about 54 minutes. After the 2004 earthquake, these oscillations were recorded by gravimeters and broadband seismometers for weeks. The entire planet was humming. Every point on Earth was moving in concert. The ground beneath New York, beneath London, beneath Tokyo, all moving together, swelling outward and settling inward in a coordinated global pulse. That is not exaggeration, that is measurement. Now, a magnitude 6.6 earthquake, the kind that happened this morning at the edge of Antarctica, does not produce detectable normal modes. It does not make the whole planet ring at its fundamental frequencies. The energy is too low by a factor of roughly 1 to 1,000. But the principle is the same. The physics is the same. The surface waves from a magnitude 6.6 still travel around the world. They still carry their energy across continents and ocean basins. They still flex every fault they pass over. They are fainter, much fainter. The ground motion they produce on the opposite side of the planet is measured in nanometers, billionths of a meter. Far below anything a human could feel, far below anything that would damage a building, far below even the detection threshold of most low-cost seismometers. But they are real, and they reach everywhere. This is the escalation, not in energy, not in danger, in understanding. The escalation is from the local view of earthquakes, an event that happens at a point and affects its surroundings, to the global view, a view where every earthquake is a planetary event, a view where the fault lines of the world are not separate. They are a single interconnected network, linked by the waves that travel between them. The escalation is in timescale as well. A single earthquake lasts seconds to minutes, but its effects on the global fault system, the nudge it delivers to every loaded fault on Earth, persists in the form of advanced clock time. That clock does not reset. Each earthquake moves the hands forward on every loaded fault by some tiny, unmeasurable amount. Over years and decades, those nudges accumulate. The background seismic field, the constant, low-level vibration of the planet from thousands of small earthquakes every day, is not random noise. It is a signal. It is the planet continuously nudging itself. Think about what that implies for a fault like the San Andreas in Southern California. The southern San Andreas has not produced a major rupture since 1857, a magnitude 7. 9 earthquake that broke more than 300 kilometers of the fault. Paleoseismic evidence shows that the average interval between major ruptures on this section of the fault is roughly 150 years, with significant variability. By that measure, the southern San Andreas is overdue. It has accumulated centuries of tectonic stress. The rocks on either side of the fault are bent, strained, loaded. At some point, possibly tomorrow, possibly in 50 years, that strain will exceed friction, and the fault will rupture. The earthquake that results will be catastrophic for the Los Angeles metropolitan area, home to more than 10 million people. Now ask yourself, does the timing of that inevitable earthquake depend only on the slow, steady accumulation of tectonic stress from the relative motion of the Pacific and North American plates? Or does it also depend, in some small, perhaps statistically detectable way, on the cumulative effect of thousands of distant earthquakes, each one sending its surface waves through Southern California and giving the San Andreas a tiny nudge? That is the question that dynamic triggering raises. And it is not a rhetorical question, it is an open scientific problem. There is a growing body of evidence that the global seismic field, the constant background vibration from earthquakes large and small, does influence the timing of earthquakes on loaded faults. The effect is small. It does not determine whether a fault will break. It determines, in some probabilistic sense, when it might break. A fault that is already at 99% of its failure stress might wait for years before reaching 100% through tectonic loading alone. But a passing surface wave from a distant earthquake, even a faint one, can add a small, additional stress, pushing the fault over the threshold slightly sooner than it would have otherwise. The earthquake was inevitable. The timing was not, and the timing is influenced in ways we are only beginning to quantify by earthquakes happening on the other side of the planet. The escalation, then, is in our responsibility. If the timing of earthquakes on major faults is influenced by distant events, then understanding that influence, quantifying it, modelling it, perhaps eventually forecasting it, becomes a public safety imperative. Not because we can stop earthquakes, we cannot. Not because we can predict them with useful precision. We cannot do that either, and the honest science says we may never be able to. But because understanding the connectivity of the fault system might allow us to refine hazard assessments, to update the probabilities, to say, with greater confidence, that after a large earthquake on one side of the Pacific, the odds of a triggered event on the other side have increased by some small but measurable amount. That is not prediction. It is probabilistic hazard assessment, and it is the direction the science is moving. Every scientific discovery creates new questions. Often, the questions are more difficult than the discovery that prompted them. Dynamic triggering is no exception. The observation that distant earthquakes can trigger local seismicity is now beyond reasonable doubt. The evidence from landers, from Denali, from the 2012 Indian Ocean earthquake, from dozens of other events, is compelling. But the mechanism, the precise physical process by which a faint passing wave nudges a loaded fault into slipping, is not fully understood. And that lack of understanding creates tension. It creates room for disagreement. It creates the conditions for scientific controversy, and that controversy is healthy. It is how science progresses. The core of the tension is simple. Seismologists agree that dynamic triggering happens. They do not agree entirely on how. Several candidate mechanisms have been proposed, each with its own evidence, its own limitations, and its own implications for hazard assessment. The most widely studied mechanism involves fluids. Most faults in the Earth's crust are not dry. They contain fluids, water, brine, carbon dioxide, often at high pressure, trapped in pores and fractures within the rock. Those fluids exert pressure on the surrounding rock. High fluid pressure reduces the effective stress holding the fault together. It makes the fault easier to slip. The technical term for this is effective normal stress reduction. A fault with high fluid pressure is, in effect, already partially unclamped. It is closer to failure than a dry fault under the same tectonic load. Now imagine a surface wave passing through that fluid-filled fault zone. The wave carries a small oscillating stress. As the wave compresses the rock, fluid pressure rises. As the wave dilates the rock, stretches it, fluid pressure drops. That oscillation in fluid pressure, small though it may be, can be enough to push a fault that is already near failure over the edge. The wave does not need to add much stress. It just needs to briefly reduce the clamping force that is keeping the fault locked. Once the fault starts to slip, the process can become self-sustaining. The initial slip reduces the friction, which allows more slip, which reduces friction further, and so on. The passing wave acts as a trigger, a small brief perturbation that initiates a much larger, self-sustaining process. This is the fluid pressure model of dynamic triggering. It has strong observational support, particularly from geothermal fields like Yellowstone and the geysers, where high fluid pressures are known to exist and where triggering is consistently observed. But the fluid model cannot explain all cases of dynamic triggering. Some triggered events occur on faults that appear to be dry, faults in crystalline basement rock with no evidence of high fluid pressures. For those cases, other mechanisms have been proposed. One involves cyclic shear fatigue. Every time a seismic wave passes through a fault zone, it imposes a small, oscillating shear stress on the fault. Most of the time, that oscillating stress does nothing. The fault is too strong or the wave too weak, but over many cycles, thousands of passages from thousands of earthquakes over years and decades, the repeated small stresses may gradually weaken the fault. They may break tiny asperities, smooth rough patches, reduce the overall strength. This is analogous to fatigue failure in metals. A paperclip bent back and forth enough times will break, even if each individual bend is far too weak to break it. The cumulative effect of many small cycles matters. The same principle may apply to faults. The background seismic field, the constant, low-level vibration from thousands of earthquakes around the world, may be slowly fatiguing fault zones, reducing their strength over long time scales. If that is true, then dynamic triggering is not just about individual large earthquakes nudging specific faults. It is about the entire global seismic field acting as a slow, continuous, planet-wide process of fatigue. That is a much more radical idea. It implies that the connectivity of the fault system is not episodic. It is continuous. The planet is always nudging itself. A third mechanism involves dynamic stress changes directly. When a seismic wave passes through a fault, it does not just oscillate fluid pressure. It also changes the stress state of the rock, the full tensor of forces acting on any given plane. Those dynamic stress changes are small, especially at great distance. But they are not zero. And for a fault that is already within a few kilopascals of its failure stress, a fault that is, in the technical language, critically stressed, even a tiny additional stress can be enough to push it over the edge. The question is whether faults commonly exist in such a critically stressed state. The evidence is mixed. Some measurements suggest that many fault systems are indeed within a few tens of kilopascals of failure. Other measurements suggest that faults are generally stronger, requiring larger stress changes to trigger. This is an active area of research. The answer matters enormously for hazard assessment. If faults are generally far from failure, then dynamic triggering is rare. If faults are generally near failure, then dynamic triggering is common, potentially very common, and the global seismic field is a major factor in earthquake timing. The tension between these models is not merely academic. It has direct implications for how we assess earthquake hazard. If dynamic triggering is primarily a fluid-driven phenomenon, then the regions most at risk are those with high fluid pressures, geothermal fields, sedimentary basins, volcanic systems. Those are relatively small areas geographically. The global triggering risk would be localized, but if dynamic triggering is primarily a fatigue phenomenon, then every fault on Earth is at risk, regardless of fluid content. The effect would be global and continuous. And if dynamic triggering is primarily a direct stress phenomenon, then the risk depends on how critically stressed the fault system is, something we do not know with any precision for most faults on Earth. This is the scientific tension at the heart of dynamic triggering. We know it happens. We do not fully understand how. And until we do, any attempt to incorporate dynamic triggering into operational earthquake forecasting will be uncertain, perhaps usefully uncertain, perhaps dangerously uncertain. The tension is compounded by a statistical problem. Dynamic triggering events are small. The triggered earthquakes are almost always magnitude 2 or less. Micro-earthquakes, far below the threshold of human perception. They are detectable only because modern seismometer networks are dense and sensitive. For every Landers or Denali or 2012 Indian Ocean earthquake, events large enough to produce a clear, unambiguous triggering signal, there are thousands of moderate earthquakes that might or might not trigger distant events. But the signal is too weak to separate from the background noise. The statistics are ambiguous. The uncertainty is large. And that uncertainty is not a failure of the science. It is a feature of the system. The Earth's fault network is complex, heterogeneous, and poorly observed in most places. Perfect knowledge is not available. The question is what to do with imperfect knowledge. There is a deeper tension as well, one that cuts to the core of how seismology is practiced and how its results are communicated to the public. The public wants certainty. It wants to know whether the ground beneath its feet is safe, whether the next big earthquake is coming, whether there is anything to do about it. Seismology cannot provide that certainty. The best it can provide is probabilities, estimates of likelihood, expressed in percentages, usually with wide error bars. Those probabilities are often misinterpreted. A 1% chance of a large earthquake in the next year does not mean it will not happen. A 99% chance does not mean it will. Probabilities are not predictions. They are descriptions of uncertainty. And the public's tolerance for probabilistic uncertainty is low, especially when the stakes are high. Dynamic triggering adds a new layer of probabilistic complexity. Even if we fully understood the mechanism, we would still face irreducible uncertainty about the state of individual faults. Is a given fault loaded? How close is it to failure? What are the fluid pressures within it? What is its fatigue history? These are not things we can measure directly over large areas. We can infer them from indirect evidence: seismic velocity, electrical conductivity, heat flow, the distribution of small earthquakes. But those inferences are uncertain. The uncertainties multiply. The result is a hazard assessment that is more complete, because it includes a real physical process that was previously ignored, but also more uncertain, because the new process introduces new unknowns. The responsible response to this tension is not to ignore dynamic triggering. It is to study it, to quantify it, to incorporate it into hazard models with appropriate uncertainty, and to communicate that uncertainty honestly. That is what good science does. It does not pretend to know more than it knows. It does not simplify for the sake of public comfort. It presents the best available evidence with all its limitations and lets the evidence guide the response. The tension is real, the uncertainty is real, but the phenomenon is also real, and pretending it does not exist, returning to the old assumption that earthquakes are independent, local events, would be a retreat from evidence. It would be unscientific, it would be irresponsible, so the scientific tension remains, and it will remain for years, probably for decades. New data will narrow the uncertainty, better models will improve our understanding. But the fundamental challenge, that we cannot observe the state of every fault on Earth directly, and that even the best indirect measurements are imperfect, is not going away. Seismology, like all Earth science, is an observational science. We cannot experiment on the planet at the scale of tectonic plates. We cannot load a fault to failure in a laboratory and watch what happens, because the timescales are too long and the force is too large. We can only observe what the planet does, build models to explain those observations, and test those models against new observations. That is the scientific method. It is slow, it is incremental, it is uncertain, but it is the only method we have. And here is the critical point. The tension, the uncertainty, the disagreement, the incomplete understanding, does not mean that dynamic triggering is not real. It is real. The observations are clear. The debates are about mechanism, not about existence. They are about the details of how the planet works, not about whether it works that way at all. That distinction matters. It matters because the public, hearing about scientific disagreement, often concludes that the science is unsettled in the sense of being unreliable, that if scientists disagree, maybe nothing is known at all. That is not how science works. Scientists disagree about the precise mechanism of dynamic triggering. They do not disagree that it happens. The phenomenon is robust. The explanation is in progress. That is normal. That is healthy. That is how science advances. The tension also creates an opportunity. It creates room for new ideas, new experiments, new ways of looking at the data. It creates incentives for better instrumentation, denser networks, longer time series. It creates a reason to revisit old data with new questions. The history of seismology is full of examples where a phenomenon that was once considered marginal or controversial turned out to be central. Plate tectonics itself was controversial until the 1960s. The idea that continents move was considered fringe by many geologists. Now it is the foundation of modern Earth science. Dynamic triggering may not be as revolutionary as plate tectonics, but it is part of the same pattern, a gradual expansion of our understanding of how the planet works, driven by better data and more careful analysis, often in the face of initial skepticism. The tension is not a sign of weakness, it is a sign of life. Let us bring the science down to the surface, down to the places where people live, work, build, raise families, go to school, down to the fault lines that run through or near major cities, fault lines that are loaded, that will eventually rupture, and that are listening to the distant earthquakes that nudge them toward their breaking point. The human consequences of dynamic triggering are not abstract. They are measured in buildings collapsed, bridges failed, roads severed, water pipes broken, gas lines ruptured, fires started, hospitals overwhelmed, and people killed or injured. The 1994 Northridge earthquake in Los Angeles, magnitude 6.7, killed 57 people, injured more than 9,000, and caused an estimated $20 billion in damage. The 1995 Kobe earthquake in Japan, magnitude 6.9, killed more than 6,000 people and caused more than $100 billion in damage. The 2010 Haiti earthquake, magnitude 7.0, killed an estimated 160,000 people. The exact number will never be known, and left more than 1 million homeless. The 2011 Christchurch earthquake in New Zealand, magnitude 6.2, killed 185 people and destroyed much of the city centre. The 2023 Turkey-Syria earthquakes, magnitude 7.8 and 7.5, killed more than 50,000 people and caused damage estimated at more than $100 billion. These are not abstract numbers. They are human lives. They are families. They are communities shattered in seconds by the sudden release of strain that had accumulated for centuries. Now add dynamic triggering to this picture. Not as a primary cause, not as the thing that creates earthquakes out of nothing, but as a modulating factor, a factor that can advance the timing of earthquakes on loaded faults, a factor that can make a fault that was already close to failure fail slightly sooner than it would have otherwise. That does not sound dramatic. A few weeks earlier, a few months, a few years. In the context of a fault that ruptures every few hundred years, a shift of a few years is geologically trivial. But for the people living on that fault, a shift of a few years can be the difference between life and death. If the next great earthquake on the southern San Andreas is going to happen in 2030, under the baseline tectonic loading, and dynamic triggering advances it to 2027, that is not a geological difference. It is a human difference. It means that people who would have been safe for 3 more years are not safe. It means that preparation that would have been completed by 2030 may not be completed by 2027. It means that infrastructure that would have been retrofitted may still be vulnerable. The difference of 3 years matters. It matters enormously. This is the human consequence of dynamic triggering. It is not that earthquakes are becoming more frequent globally. The global rate is stable. It is not that dynamic triggering is creating new earthquakes that would not have happened otherwise. The evidence suggests that triggered earthquakes are almost always small, and that even when triggering advances the timing of a large earthquake, that earthquake was going to happen anyway. The consequence is not more earthquakes. The consequence is timing. And timing is everything when it comes to disaster preparedness. Consider a city like Istanbul. Istanbul straddles the North Anatolian Fault, a major strike-slip fault similar to the San Andreas. The fault has produced a sequence of large earthquakes over the past century, migrating westward. The last major rupture in the sequence was the 1999 Izmit earthquake, magnitude 7.6, which killed more than 17,000 people. The next segment west of Izmit lies directly beneath the Sea of Marmara, just south of Istanbul. Seismologists estimate the probability of a magnitude 7 or larger earthquake on that segment within the next 30 years at somewhere between 30 and 60%, depending on the model. That is a high probability. It is a near certainty over longer timescales. Istanbul is a city of 15 million people, built largely on soft sedimentary soils that amplify shaking. The infrastructure is aging. Many buildings are not earthquake resistant. A large earthquake near Istanbul would be catastrophic. The human consequences would be staggering. Tens of thousands dead. Hundreds of thousands homeless. Economic disruption, measured in hundreds of billions of dollars. Now ask yourself, does the timing of that inevitable earthquake depend, in any measurable way, on the global seismic field? On the surface, waves from distant earthquakes passing through the North Anatolian Fault and giving it tiny nudges? The honest answer is that we do not know. The effect is likely small. The tectonic loading rate on the North Anatolian Fault is relatively high, about 2 centimeters per year, so the fault accumulates stress quickly. A small nudge from a distant earthquake is unlikely to advance the clock by more than a few weeks or months relative to the decades-long loading cycle. But few weeks or months is not nothing. if the nudge advances the earthquake by 6 months, and the earthquake was going to happen in 2032, it now happens in 2031. That is 1 less year of preparation, 1 less year of retrofitting, 1 less year of public education, emergency planning, infrastructure investment. The difference matters. There is a second-order human consequence as well, and it is more subtle but potentially more significant. Dynamic triggering may affect not just the timing of earthquakes but their size. This is speculative. The evidence is limited, but it is worth considering. When a seismic wave passes through a fault zone, it does not just add a small static stress. It adds an oscillating dynamic stress. That oscillation might affect the rupture process itself. If the dynamic stress arrives at the same time as the rupture is beginning, if the wave and the rupture are in phase, it could, in principle, increase the slip or extend the rupture length. The triggered earthquake could be larger than it would have been without the triggering. This is not proven. It is a hypothesis, supported by some observations and some numerical models. But if it is true, the implications are profound. It would mean that not only the timing but the magnitude of earthquakes could be influenced by distant events. The earthquake that destroys a city might be larger, perhaps significantly larger, because of a nudge from an earthquake on the other side of the world. That is a worst-case scenario. It is also, at this point, a low-probability scenario. The evidence is not strong enough to treat it as established, but it is strong enough to warrant further investigation. The human consequences of dynamic triggering also intersect with communication. How do you tell people that the earthquake risk in their city is influenced by earthquakes happening on the other side of the planet? How do you convey that the probability of a large earthquake in the next year has increased slightly because of a magnitude 7 event in a remote ocean, and that the increase is real but too small to change individual behaviour in any meaningful way? How do you avoid panic while maintaining honesty? How do you avoid complacency while avoiding fear? These are not trivial questions. They are at the heart of the challenge of communicating earthquake science to the public. The public wants simple answers. Science does not provide them. The tension between the complexity of the science and the simplicity of public communication is real, and it has consequences. Poor communication can lead to panic, which can lead to economic disruption, which can lead to people taking actions that make them less safe. Poor communication can also lead to complacency, to people ignoring warnings because the language is too hedged, too probabilistic, too uncertain. Finding the right balance is difficult. It is an ongoing challenge, and dynamic triggering makes it more difficult. There is another category of human consequence that is often overlooked. It is not about death and destruction. It is about the slow, cumulative erosion of the sense of security that comes from believing the ground beneath your feet is stable. Most people do not think about earthquakes most of the time. They live their lives, they go to work, they raise their children, they plan for the future. The possibility that the ground might shake violently and destroy everything they have built is not part of their daily experience. That is healthy. Living in a state of constant vigilance is not sustainable. But there is a difference between healthy disregard and willful ignorance. And dynamic triggering, the knowledge that the planet is constantly, invisibly nudging itself, has the potential to shift that balance. Not for everyone. Most people will never hear of dynamic triggering, or will hear of it and forget it. But for those who do understand it, for those who really absorb what it means, the ground changes. It becomes less solid, less certain, less reliable. That loss of certainty is a human consequence. It is not measured in dollars or deaths. It is measured in a subtle, hard-to-articulate shift in how you inhabit the world. You stand on the ground and you know, really know, that it is not still, that it is in motion, that it is listening, that it may answer at any moment. That is not fear. It is awareness, but it is a different kind of awareness than most people carry. The responsible way to hold this awareness is not to let it become anxiety. It is to let it become action, to support earthquake preparedness, to retrofit buildings, to secure water heaters and bookshelves, to have an emergency kit, to know what to do when the shaking starts. These are not onerous tasks. They are not expensive. They are not time-consuming. But they save lives. The evidence is clear. In the 2011 Christchurch earthquake, buildings that had been retrofitted performed dramatically better than those that had not. In the 1995 Kobe earthquake, the difference between life and death was often a matter of building codes and construction quality. Preparedness works. It is the single most effective intervention for reducing earthquake risk, and the knowledge that dynamic triggering exists, that the planet is more connected than we thought, should be a motivation for preparedness, not a source of paralysis. The earthquakes are coming. That has always been true. The only question is when. Dynamic triggering does not change that fundamental fact. It only adds a layer of complexity to the timing. But the solution is the same regardless. Prepare, retrofit, plan, practice. The solution does not depend on knowing exactly when the earthquake will happen. It depends on being ready when it does. No fault is an island. That is the central insight of dynamic triggering, and it is the key to understanding the cascading effects that connect earthquakes across the planet. But the cascades do not stop at the fault system. They propagate outward, into the oceans, into the atmosphere, into the biosphere, into the human systems built on top of the Earth's surface. An earthquake is not just a rupture. It is a disturbance that radiates through multiple Earth systems simultaneously. The seismic waves are the fastest expression of that disturbance, travelling at kilometres per second, but they are not the only expression. The rupture displaces the seafloor, generating tsunamis that travel at hundreds of kilometres per hour across ocean basins. It changes the stress field in the surrounding crust, influencing the timing and location of aftershocks. It triggers landslides, destabilizing slopes and sending debris into rivers and reservoirs. It disrupts groundwater systems, changing well levels and stream flows. It releases gases, radon, carbon dioxide, methane from the fractured rock. It generates infrasound and atmospheric gravity waves that propagate upward into the upper atmosphere, where they can be detected by satellites. The cascading effects of a large earthquake are planetary in scale and multi-system in scope. Dynamic triggering adds another layer to this cascade. It extends the reach of the earthquake beyond the immediate rupture and beyond the well-known effects of tsunamis and landslides. It reaches across the planet, through the solid Earth, and touches faults on the other side of the world. Those distant faults, if they are loaded, may rupture in turn. Not immediately, not deterministically, but with an elevated probability. And those triggered earthquakes produce their own cascades, their own tsunamis, landslides, groundwater changes, atmospheric waves. The cascade propagates through the fault system as a wave of elevated probability, spreading outward from the original rupture at the speed of seismic surface waves. This is not a deterministic chain reaction. Most distant faults will not rupture, but some will, and those that do will send their own waves outward, potentially triggering further events. The system is coupled, it is globally connected. The cascade is real. The most dramatic example of cascading triggering in the modern instrumental record is the 2012 Indian Ocean earthquake sequence. On April 11, 2012, a magnitude 8.6 strike-slip earthquake struck off the coast of Sumatra. It was the largest strike-slip earthquake ever recorded, but it was not alone. 2 hours later, a magnitude 8. 2 aftershock occurred on the same fault system, and over the following days, seismicity was elevated globally. The global earthquake rate increased by roughly 30% for nearly a week. the triggered earthquakes were scattered across the planet. In Mexico, in Japan, in the Pacific Northwest, in the Mid-Atlantic Ridge. The cascade was global. The statistical signal was clear enough that the researchers who published the study, the definitive study of the 2012 sequence and its global triggering effects, could say with confidence that the event had increased the probability of earthquakes on faults worldwide. The increase was small. The baseline probability of a large earthquake on any given fault on any given day is tiny. A 30% increase of a tiny number is still tiny, but the effect was real. The cascade had happened. The 2012 sequence also demonstrated something important about the relationship between triggering and fault type. The triggered earthquakes were not distributed uniformly across all fault types. They were concentrated on strike-slip faults, the same fault type as the triggering event. That makes sense. Strike-slip earthquakes radiate strong surface waves, particularly love waves, which are horizontally polarized shear waves. Those love waves are efficient at stressing other strike-slip faults because the wave motion aligns with the fault motion. A love wave passing through a strike-slip fault shakes the fault in the direction it is already trying to move. That is resonance in the mechanical sense. The wave aligns with the natural tendency of the fault, making triggering more likely. This is not speculation. It is observed. The 2012 sequence triggered strike-slip faults preferentially. The signal was clear. This preferential triggering has implications for how we think about cascading effects. If triggering is most efficient between faults of the same type, then the cascade is not random. It is structured by the global distribution of fault types. The Pacific Ring of Fire is dominated by subduction zones, thrust faults where one plate dives beneath another. Subduction zones produce the largest earthquakes, but they are less efficient at generating love waves than strike-slip faults. Strike-slip faults, like the San Andreas, the North Anatolian, the Alpine Fault of New Zealand, and the Mid-Ocean Ridge Transform faults, are the primary sources of the surface waves that travel farthest and trigger most efficiently. So the cascade tends to flow from strike-slip faults to other strike-slip faults. The great thrust earthquakes of the Ring of Fire, while devastating locally, may have less global triggering reach than a magnitude 6.6 strike-slip event on a mid-ocean ridge. That is counterintuitive. A magnitude 8.5 thrust earthquake releases many times more energy than a magnitude 6.6 strike-slip. But the energy is packaged differently. The strike-slip event puts more of its energy into the surface waves that travel the farthest. It is more efficient at global triggering, size for size. The 6 at the edge of Antarctica this morning is a strike-slip event. It is the same family as the 2012 monster, scaled down by a factor of roughly 1,000 in energy. Its surface waves are fainter, but they are the right kind of waves to trigger other strike-slip faults around the world. Now, consider the cascade beyond the solid Earth. The same surface waves that trigger distant earthquakes also interact with the ocean. In the deep ocean, away from coastlines, the ground motion from a passing surface wave is tiny. Microns or less. That ground motion couples into the water column, generating acoustic waves that travel through the ocean at the speed of sound in water, about 1.5 kilometers per second. Those acoustic waves are far too faint to be heard by human ears, but hydrophones, underwater microphones, can detect them. The global hydrophone network, originally built to monitor for nuclear testing, routinely detects the acoustic signatures of distant earthquakes. The sound of a magnitude 6.6 earthquake at the edge of Antarctica travels through the deep ocean, around the planet, and is recorded at listening stations in the Indian Ocean, the Atlantic, the Pacific. The ocean rings too. It rings with the same seismic surface waves that ring the solid Earth. The two are coupled. You cannot shake the Earth without shaking the ocean. and you cannot shake the ocean without affecting everything that lives in it. The effects on marine life are poorly understood but potentially significant. Many marine organisms detect vibrations and pressure changes. Fish have lateral lines that sense water motion. Whales produce and hear low-frequency sounds that can travel thousands of kilometers through the ocean. The low-frequency surface waves from a large earthquake produce pressure fluctuations in the water column that are within the hearing range of baleen whales. Do the whales hear the earthquakes? Almost certainly. Do they respond? There are anecdotal reports of unusual whale behavior following large earthquakes. But systematic studies are lacking. The signal is faint, the ocean is noisy. Disentangling earthquake-related behavior from normal behavior is difficult. But the question is worth asking. The Earth's systems are coupled. A rupture on the seafloor produces seismic waves that travel through the solid Earth and couple into the ocean, producing acoustic waves that travel through the water and are detected by marine organisms. The cascade does not stop at the shoreline. It goes underwater. It goes into the biosphere. The atmosphere is also part of the cascade. Large earthquakes generate infrasound, sound waves with frequencies too low for human hearing, that propagate upward through the atmosphere. As the seismic surface waves pass through the ground, they couple into the air above, generating acoustic waves that travel upward at the speed of sound. Those infrasonic waves can reach the ionosphere, the electrically charged layer of the upper atmosphere, where they produce detectable disturbances in electron density. Satellites can see the signature of a large earthquake in the ionosphere, minutes after the rupture. The 2011 Tohoku earthquake in Japan produced clear ionospheric disturbances that were detected by GPS satellites. The earthquake had reached space. The cascade had gone from the seafloor to the upper atmosphere in less than 10 minutes. The planet is a single system. The boundaries between solid Earth, ocean, and atmosphere are not barriers. They are interfaces across which energy flows. An earthquake is not a geological event. It is a planetary event, affecting all the Earth's fluid envelopes simultaneously. The cascading effect sets do not stop at the natural world. They extend into human systems, into infrastructure, into economies, into social stability. A large earthquake near a major city destroys buildings, roads, bridges, ports, airports. It disrupts supply chains, halts manufacturing, closes schools, shuts down hospitals. It displaces populations, creating refugee flows that strain neighbouring regions. It can trigger fires, chemical spills, dam failures, nuclear accidents. The 2011 Tohoku earthquake triggered the Fukushima Daiichi nuclear disaster, which released radioactive material into the environment and displaced more than 100,000 people. The earthquake did not cause the disaster directly. The tsunami did. The earthquake generated the tsunami, and the tsunami overwhelmed the plant's defences. A cascade within a cascade. A rupture on the seafloor, a displacement of the water column, a wave travelling across the Pacific, a seawall overtopped, a cooling system failed, a meltdown, an evacuation, a region contaminated. One event, cascading through multiple systems, geological, oceanographic, engineering, social, political, producing consequences that are still unfolding more than a decade later. Dynamic triggering adds to this cascade by extending the reach of the initial rupture. The earthquake that triggers a distant event may be far from any population centre. The 6.6 at the edge of Antarctica this morning is a perfect example. It is in the middle of nowhere. Its local effects are negligible. It will not generate a tsunami. It will not damage anything. It will not hurt anyone. But its surface waves are travelling around the world and they are passing under loaded faults. If one of those loaded faults is near a major city, if the San Andreas, or the North Anatolian, or the Alpine Fault, or the Enriquillo Plantin Garden Fault in Haiti, receives a nudge from this morning's earthquake that advances its clock by a week or a month or a year, the cascade will have connected an empty stretch of ocean to a densely populated city. The connection is invisible, it is unmeasurable in any individual case. But it is real. The energy that started at the bottom of the world ended up, via the surface waves, as a small additional stress on a fault beneath a city. And if that fault ruptures tomorrow, or next month, or next year, the cascade will have been completed. The chain of causation will run from the empty ocean to the collapsed buildings through the physics of wave propagation and the mechanics of fault loading. That is not fear-mongering. That is physics. It is the unavoidable consequence of a globally connected fault system. The earthquakes of the world are not separate. They are one system, and the system cascades. The challenge is that we cannot see the cascade in real time. We can observe the surface waves travelling. We can observe the distant triggered micro-earthquakes. We can measure the statistical increase in global seismicity after a large event. But we cannot look at a given fault and say, this fault was nudged by that earthquake, and that nudge advanced its clock by this many days. The signal is too faint, the noise is too large, the uncertainties are too great. So the cascade remains, for now, a statistical phenomenon. It is visible in aggregate, over many events, over long time periods. It is not visible in individual cases. That is frustrating. It is also scientifically interesting. It means that the cascade is real but stochastic, governed by probabilities, not by deterministic chains of cause and effect. The Earth is not a row of dominoes. It is a network of interconnected elements, each with its own threshold, each subject to random fluctuations, each responding probabilistically to perturbations. That is a different kind of system. It is more complex, harder to predict, and more resilient to individual perturbations. The cascade does not propagate in a straight line. It propagates as a diffuse wave of elevated probability, spreading through the fault network, gradually fading as it spreads. Most perturbations do nothing. Some produce small responses. Very rarely, in a configuration that aligns just right, a perturbation might contribute to a large response. But that large response is always the result of the local state of the fault, the accumulated tectonic stress, not the distant perturbation alone. The distant perturbation is a trigger, not a cause. The cause is the slow, inexorable motion of the tectonic plates. The trigger is a small, brief, faraway nudge. The cascade amplifies the trigger but does not replace the cause. That is the final, most important layer of the cascade. It does not create new earthquakes. It only advances the timing of earthquakes that were already inevitable. Standing at the present moment, looking forward, what do we see? What does the science of dynamic triggering tell us about the future of earthquake hazard on a globally connected planet? The honest answer is that it tells us less than we would like and more than we once knew. The future projections are not predictions. They are scenarios, plausible outcomes based on current understanding, with wide ranges of uncertainty. They are tools for thinking, not forecasts to bet on, but they are the best tools we have, and they point in a clear direction, toward a future in which earthquake hazard assessment is probabilistic, globally aware, and continuously updated. One projection is that dynamic triggering will be incorporated into operational earthquake forecasting. Operational forecasting is the practice of issuing time-dependent probabilities of earthquake occurrence. The chances of a large earthquake in a given region over a given time window based on current conditions. The United States Geological Survey already produces operational forecasts for California, including aftershock forecasts after large earthquakes. Those forecasts are based on statistical models that incorporate the static stress changes from the main shock, the permanent redistribution of stress that influences aftershock locations. They do not currently incorporate dynamic triggering from distant earthquakes. The scientific basis is not yet strong enough. The uncertainties are too large. The statistical signals, while real, are too weak to support operational use. But that may change. As the global seismometer network improves, as the catalogue of earthquakes grows longer, as the statistical methods become more sophisticated, the signal of dynamic triggering may become clear enough to be useful. A future operational forecast might include, after a large strike-slip earthquake anywhere in the world, a small but measurable increase in the probability of triggered earthquakes on other strike-slip faults globally. That increase would be too small to change individual behavior. A 1% increase in probability is not a reason to change daily plans, but it could inform infrastructure operators, emergency managers, and other users who make decisions based on small changes in risk. The future of earthquake forecasting is probabilistic. Dynamic triggering is part of that probabilistic future. A second projection involves the long-term cumulative effects of dynamic triggering on earthquake statistics. The global earthquake rate is stable over decadal timescales, but that stability may mask variability induced by dynamic triggering. The question is whether dynamic triggering can influence the timing of large earthquakes on major faults, the magnitude 7 and 8 events that cause catastrophic damage. The evidence so far suggests that it can, but that the effect is small. The 2012 Indian Ocean earthquake, the largest strike-slip event ever recorded, produced a clear global triggering signal. But the triggered events were small. No magnitude 7 or 8 earthquakes were clearly triggered by the 2012 event. The statistical increase in global seismicity was dominated by micro-earthquakes. That pattern, small events triggered, large events not, has held across all well-documented cases of dynamic triggering. It suggests that dynamic triggering is effective at nucleating small ruptures, but that large ruptures require a more specific configuration of local stress, fluid pressure, and fault geometry. The trigger can only work if the fault is already extremely close to failure. Most faults are not that close. Even after a large triggering event, the probability of a triggered large earthquake remains very low. So, the long-term cumulative effect of dynamic triggering on the global rate of large earthquakes is likely small. It may advance the timing of some large earthquakes by months or years relative to a baseline of centuries. It does not change the long-term average frequency. The tectonic loading sets the average. The dynamic triggering jitters the timing around that average. A third projection involves the interaction between dynamic triggering and climate change. This is a new and emerging area of research, and it is important to be careful. The link between climate change and earthquakes is indirect and uncertain. Climate change does not directly cause earthquakes, but climate change alters loads on the Earth's crust. Through melting ice sheets, changing water storage in reservoirs, altering ocean circulation patterns. Those load changes can influence the stress state of faults. The weight of an ice sheet depresses the crust beneath it. When the ice melts, the crust rebounds. That rebound changes the stress field, potentially triggering earthquakes on nearby faults. This is not speculation, it is observed. In Scandinavia and Canada, regions that were covered by thick ice sheets during the last ice age, the ongoing glacial rebound is associated with elevated seismicity. The earthquakes are small, but they are real. They are triggered by the unloading of the crust as the ice melts. Now consider the present. The Greenland ice sheet is melting. The West Antarctic ice sheet is melting. The glaciers of Alaska, Patagonia, the Himalayas, the Alps, the Andes, all are melting. The total mass of ice lost from the Earth's land surface is staggering, hundreds of billions of tons per year. That mass is being redistributed from the ice sheets to the oceans. The crust is rebounding, the stress field is changing. And those stress changes, though slow, are occurring on timescales of decades to centuries, fast enough to matter for earthquake hazard. The question is whether the changing stress field from ice melt can interact with dynamic triggering. Could a passing seismic wave from a distant earthquake trigger an earthquake on a fault that is already more loaded than usual because of ice melt? Could the combination of glacial rebound and dynamic triggering advance the timing of an earthquake that would otherwise have occurred centuries later? The honest answer is that we do not know. The research is in its early stages, but the question is worth asking. The Earth's systems are coupled. Climate change is altering one of those systems, the cryosphere, and that alteration is propagating through the coupled system, potentially reaching the fault network. The future projections must include these interactions, even if the uncertainties are large. A fourth projection involves monitoring. The future of dynamic triggering research depends on better monitoring, denser seismometer networks, longer time series, higher sensitivity instruments, faster data processing. The global seismometer network has improved dramatically over the past 3 decades, but large gaps remain. The oceans are particularly poorly monitored. Most of the Earth's surface is ocean, but most seismometers are on land. The mid-ocean ridge system, the largest geological feature on the planet, the source of countless earthquakes, is sparsely instrumented. We see the earthquakes that occur there, we locate them, we measure their magnitudes, but we see them through a fog. The signals are distant, attenuated, and the fine detail is lost. A denser ocean bottom seismometer network would transform our understanding of mid-ocean ridge earthquakes and their triggering potential. Similarly, improved monitoring of the continental interiors, the stable cratons where large earthquakes are rare but not impossible, would help resolve the question of whether dynamic triggering occurs everywhere or only in tectonically active regions. The future of dynamic triggering science is a future of better data. The questions that remain open today will be answered, or at least narrowed, by the data that are collected tomorrow. That is the rhythm of science. Observation first, theory second. Refinement always. A fifth projection involves public communication. As the science of dynamic triggering matures, the challenge of communicating it to the public will not diminish. It will grow. The public will hear about dynamic triggering. They will encounter it in news articles, social media posts, YouTube videos. Some of those sources will present it accurately. Many will not. The gap between the scientific reality, faint signals, small effects, high uncertainty, probabilistic statements, and the public demand for simple, dramatic narratives is large. It is not going away. The future of dynamic triggering communication is a future of repetition, of restating the same caveats over and over, of resisting the temptation to overstate, of accepting that some fraction of the audience will always misunderstand. That is frustrating. It is also necessary. The alternative, simplifying to the point of inaccuracy, exaggerating to the point of fear-mongering, is worse. It erodes trust. It leads to bad decisions. It makes the world less safe. The future of dynamic triggering science depends on trust. Trust between scientists and the public. Trust between scientists and policymakers. Trust between scientists and the media. That trust is earned through honesty, through acknowledging uncertainty, through refusing to overstate, through saying, again and again, we do not know everything, and this is what we do not know. That is not a weakness. It is the foundation of scientific authority. The final projection is the most speculative and the most important. It is not about dynamic triggering itself. It is about the worldview that dynamic triggering represents. The worldview of a connected planet. A planet where boundaries between tectonic plates, between ocean and atmosphere, between natural and human systems, are not barriers. They are interfaces. They are places where energy and information flow from one system to another. The future of Earth science is a future of integration, of understanding the planet as a single, coupled system, not a collection of separate domains. The geologist, the oceanographer, the atmospheric scientist, the biologist, the social scientist. They will need to work together, share data, build models that cross traditional boundaries. Dynamic triggering is one example of why that integration matters. A rupture on a mid-ocean ridge generates seismic waves that travel through the solid Earth, couple into the ocean as acoustic waves, propagate into the atmosphere as infrasound, disturb the ionosphere, and reach the fault beneath a city on the other side of the world, where it may advance the timing of an earthquake by a small, unmeasurable amount. That is one cascade. There are others. They are all around us, operating continuously below the threshold of perception, connecting the planet into a single, humming, restless whole. The future of Earth science is to map those connections, to measure them, to model them, and to understand them well enough to live wisely on the surface of this moving, breathing planet. The future is not about prediction. It is about understanding. And understanding is the beginning of wise action. Let us return to where we began. To the ground beneath you. To the continuous shell of rock that is the outer surface of the planet. To the fragments that make up that shell, the tectonic plates, and to the boundaries between them, where the plates interact, lock, strain, and release. To the earthquakes that are the signature of that release. And to the waves that travel outward from every earthquake, carrying its energy across the planet, through the deep interior and along the surface, reaching every other fault on Earth. Consider the magnitude 6.6 earthquake that struck this morning at the edge of Antarctica. On the map of human concerns, it is nothing. It broke no buildings. It injured no one. It generated no tsunami. It did not make the news. By the standards that govern what we pay attention to, it was a non-event. But the planet does not measure earthquakes by the standards of human news. The planet measures them by the standards of physics. And by those standards, this morning's earthquake was a planetary event. Its P waves travelled through the mantle, through the outer core, through the inner core, emerging on the opposite side of the Earth. Its S waves sheared the rock of the mantle, stopping at the core mantle boundary where the liquid outer core absorbed them. Its surface waves, the love waves and Rayleigh waves that carry the earthquake's long-range reach, rolled outward across the Pacific, across the Indian Ocean, across the Atlantic, around the entire planet. They passed under South America, under Africa, under Asia, under North America, under Europe, under Australia, under Antarctica itself, the continent whose edge was the source. They passed under the city where you are sitting. They passed under every fault on Earth. Every loaded fault, every fault that has been accumulating tectonic stress for decades or centuries, received a nudge this morning. A tiny nudge. A nudge far too small to measure, far too small to feel, far too small to matter in any individual case. But a nudge, a real nudge. The clock on every loaded fault on Earth was advanced this morning by an amount that we will never know. That is the reframe. That is the lens through which this documentary asks you to see the planet. Not as a collection of separate places, separate earthquakes, separate risks, but as a single system. A system in which every rupture is felt everywhere. A system in which the ground beneath your feet is in constant, invisible conversation with earthquakes happening on the other side of the world. A system in which the timing of the next great earthquake in your city may depend, in some small probabilistic way, on a rupture that occurred this morning in a stretch of ocean so remote that most maps do not bother to label it. This is not a reason for fear. It is a reason for awareness. The earthquakes are coming. They have always been coming. The tectonic plates move. The faults load. The strain accumulates. The release is inevitable. That has been true for millions of years. It will be true for millions more. Dynamic triggering does not change that fundamental fact. It only adds a layer of complexity to the timing, a layer of global connectivity that was not fully appreciated until the 1990s and is still being mapped, measured, and modelled. The awareness that dynamic triggering provides is not the awareness that earthquakes are more frequent or more dangerous. They are not. The global rate is stable. The hazard is what it has always been. The awareness is that the system is connected, that the earthquake that destroys a city may have been nudged, advanced in time, by an earthquake that occurred far away, in a place no one was watching, at a time no one remembers. The earthquake is the same, the damage is the same, the death toll is the same, but the story is different. The story is planetary. The earthquake did not happen only there, it happened everywhere. The rupture had a location. The event did not. This reframe has implications for how we live. Not in the sense of dramatic changes. We cannot stop tectonic plates from moving. We cannot prevent earthquakes. We cannot predict them with useful precision. The limitations of earthquake science are real, and they are not going to be overcome by better understanding of dynamic triggering. But the reframe does change something. It changes the mental map. It replaces the map of isolated events with the map of a connected system. On the connected map, the distinction between local and distant earthquakes is blurred. Every earthquake is local in the sense that its waves reach you. Every earthquake is distant in the sense that its rupture is somewhere else. The ground beneath you is not separate from the ground beneath the ocean at the edge of Antarctica. It is the same ground, the same continuous shell of rock, the same single planetary object. When that shell is struck anywhere, it vibrates everywhere. You are standing on the bell. The bell is being struck constantly. You do not feel most of the strikes because they are too faint, too distant, too high frequency for your body to detect. But they are real. They are happening. They are part of the background of your life, as constant and as invisible as the rotation of the Earth or the orbit of the Moon. The final reframe, then, is a reframe of attention. We pay attention to earthquakes that break things. That is natural. That is sensible. That is how the news works, how emergency management works, how disaster response works. But the planet pays attention to all earthquakes. The planet registers every rupture, every slip, every release of strain. The planet answers every earthquake with its own response. Surface waves travelling around the world, passing under every fault, nudging every loaded clock. The planet is always listening. The question is whether we are willing to listen with it. Not to every individual earthquake. There are too many, most are too small, the signal is too faint. But to the pattern, to the aggregate, to the statistical reality, that the faults of the world are not separate, they are one system, and the system is always in motion. Stand outside tonight if you can, stand on the ground, feel its solidity, its permanence, its refusal to move under your weight. That solidity is real. It is the reason you can stand, walk, build, live. But beneath that solidity, beneath the threshold of your senses, the planet is in motion. The plates are moving. The faults are loading. The earthquakes are happening. Somewhere, every day, thousands of them, most too small to feel, some large enough to record, a few large enough to matter. And the waves are travelling. Every earthquake sends its waves across the planet. Every fault receives them. The conversation is constant. The planet is ringing. It was ringing this morning, when the fault at the edge of Antarctica tore open. It is ringing now, as you watch this. It will be ringing tomorrow, and the day after, and the day after that. The ringing will never stop. It is the sound of a living planet, not alive in the biological sense, alive in the geological sense, active, dynamic, restless, never still. The ground beneath you is not dead. It is not static. It is not finished. It is in motion. It has always been in motion. It will always be in motion. And every motion, everywhere, is felt everywhere else. That is the planet. That is the system. That is the ground you stand on. Listen, it is talking. It has always been talking. you just were not listening for the right thing. This morning, a magnitude 6. 6 earthquakes struck at the edge of Antarctica. By the standards of the news, it was a non-event. By the standards of the planet, it was another note in a conversation that never ends. Somewhere on Earth tonight, a loaded fault received that note. Somewhere on Earth tonight, a clock advanced. Somewhere on Earth tonight, the planet is still deciding how it will answer.